Okay, so probability generating functions. These are functions that encode everything you need to know about a random variable. However, the random variable has to be discrete, and for simplicity, let me assume that it takes values in the integer 0, 1, 2, etc. So I have a random variable x, and it will have some probabilities, right? Some masses. So let's give a name to those masses. So pk is the probability that x is k for k equals 0, 1, 2, etc. So these are non-negative numbers and add up to 1. And then the generating function probability generating function, which I'm going to call g sub x, and I like to use the variable z, is the power series associated to the sequence. So k goes from 0 to infinity, pk z to the k. Okay. You can also, if you think of these as probabilities and this as k, the value of x, you can also think of this as the expectation of the function z to the power of x. Where you think of z as being fixed, z to the power of x is a function of x, and this is the expectation of that function of x. So that's probability generating function. Now, these have several nice properties. For instance, being an infinite series, you might worry about when does it converge. G of x actually converges, always converges for absolute value of z less than 1. This can be seen easily using the triangle inequality, because you can put the absolute values inside using the triangle inequality, and then when z is less than 1, that will be less than pk, which adds up to 1. Right? So that's the first property. Also, because it's a power series that converges, it's fairly easy to show that you can take derivatives of all orders. So the g of x is infinitely differentiable for z less than 1. And when you take the derivatives and evaluate them at 0, you recover what are called the Taylor coefficients, and the probabilities pk are exactly the Taylor coefficient. So this is the way to go back and forth. If you give me a random variable with a certain mass distribution, you can build the generating function. Conversely, if you have the generating function, you can take its derivatives, plug it in at 0, and you recover the probability, the mass distribution. Okay, so now let me do a few simple examples, just to warm up a little. Suppose x is a binomial, and p. Right? What is the probability generating function in that case? Well, you have to sum from 0 to n, because that's the range of a binomial distribution, and then you have to do pk 0 to the k. So pk is n choose k p to the k 1 minus p to the n minus k times 0 to the k. Now p and z can be joined together under the power, and then by the binomial theorem this becomes pz plus 1 minus p to the n. So the generating function is just this function here. Okay, now the situation at 0 is clear. What about at 1? So when you plug in 1, you get the sum of the pk's, which we know has to adapt to 1, right? So that's pretty easy. But in fact, and here is where a little bit of theory is needed, but one can justify taking higher derivatives at 1 as well. Okay, so let's compute the derivative g prime, and let's just do it term by term, right, with the power rule. So it's going to be the sum. Now k equal to 0 is constant, 0 to 0 is 1. When you take the derivative, that goes away, so we don't have that. But otherwise we have k pk z to the k minus 1. And here, if we now evaluate at 1, we get some k pk, but that's exactly the expectation of x. Okay, so we can recover the expectation by taking the derivative, and if we take further derivatives, we'll get higher and higher moments of the random variable. The moments are the expectation of powers of x. One of the very nice facts that probability generating function satisfy is the following. If you have two random variables x and y that happen to be independent, right, then the generating function of the sum is just the product of the generating function. The proof is actually quite easy, right? So let's think of it in terms of this formulation as the expectation of 0 to the k, 0 to the x. So this left hand side is the expectation of z to the x plus y, right, which I can write as the expectation of z to the x times z to the y. But x and y are independent, so and this is a function of x and this is a function of y. I can split the expectation up, right? Expectation of z to the x times expectation of z to the y. And so that's, this is the one-line verification. Another interesting fact has to do with random sums. So suppose I have a sequence of independent, identically distributed random variables, and these are all distributed like some variable x. And let's assume that n is a random time, so it takes values in the indices here, 1, 2, etc. So n it should be independent of everything. Okay. Now let's take the random sum, where you sum x1 all the way up to xn. Okay. Well, then the generating function for s is actually the composition of the generating function for n and the generating function for x, this random variable that they are all equal to in distribution. So remember, composition means that you take g of n and you plug in g of x. Okay, this is the proof of this is not a one line, but almost. And we just have to condition. So g of s is the expectation of z to the x1 all the way to xn, and it's good to condition on the possible values of n. So let's take little n from 1 to infinity, and now let's assume that big N is equal to little n times the probability that this is little n. But remember, this event here is independent of these, right? This was an independent random time, so that cancels out. Can remove it. And then these becomes products here. These sums become products of z to the x1, z to the xn. But they are independent. So we can then apply fact 1 and we get a product of expectations. And they're all the expectation of z to the x to the power n. And so that's exactly gn evaluated at z to the x.